Okay, since we have now Ex given by k lambda cosine theta dy divided by x squared plus y squared, we have to be careful to go from theta to y. We can do that because cosine theta is x over square root of x squared plus y squared. So we can write cosine theta like that, so that we can get an integration in terms of y only, which is this. Since x is constant, I'm taking outside k lambda x, okay, integral sign, cosine theta is this. So we have exactly the same square root as this one, so that you will end up with dy over cube root of x squared plus y squared, which is a very difficult integration. This is not easy. Okay, we cannot use change of variable. If we had here like y dy or some y square dy or something, we could easily integrate this, but not in this case, because if we change the variable from y to u, we won't have a factor of y on the top, so that this is very difficult integration. So there is no way that we can solve this at this stage. So, but now, can I go to the angle integration? Can I do this? Okay. So, as you see, we have this factor and we will be able to use this. You know, since we are going to the theta integration, in other words, we will have the integral something times d theta. This is an angle integration. So what are we going to put it here? First of all, we have to go from dy to d theta, okay? But in order to do this, we have to get an expression for including y. And as you see, the tangent theta is simple because it is equal to y over x. So y equals x times tangent theta, okay? But if you take dy from here, okay, since x is constant, we will have x d theta divided by cosine square theta, because the derivative of tangent theta is just 1 over cosine square theta, or secant square theta, okay? X secant square theta d theta, okay? So instead of dy now we can write this. So this is handled. So we have, or this one actually. This one is better because it will cancel one of the cosine square theta on the denominator. So what about this? As you see, look at this expression. Cosine theta is x over square root of x squared plus y squared, but we have 1 over x squared plus y squared. So it means that if you get this expression, you see that cosine square theta divided by x squared will be exactly, okay, so put this to the denominator, 1 over just x squared plus y squared, okay? So 1 over x squared plus y squared will be 1 over x plus y squared will be just, okay, will be just equal to cosine square theta over x squared. So now this ex will be equal to k lambda. Now cosine theta is there. I'm not touching it, as you see, but dy is coming from here. X d theta over cosine square theta, x over cosine square theta d theta, okay? Everything divided by this, but this is just cosine square theta divided by x square theta. In other words, instead of 1 over x squared plus y squared, I can write just directly cosine square theta over another term, which is here, okay, cosine square theta divided by x squared. But it's very nice because these cosine square thetas will cancel each other, and one of the x's will cancel each other, so that we will have just x, okay? So it will be k lambda over x, okay? Integral, the only thing which remains inside the integral sign will be cosine theta d theta. Wow, it turned out to be a very simple integration, as you see, okay? So now, in this case, we have to put the limits for these angles, okay? Don't forget, for this one, for instance, the angle is very small, but when you go to upper direction, okay, in positive y direction, these small segments, when you consider all these segments, the angle, as you see, this angle will be near to pi half, 90 degrees, for infinitely long distances. Similarly, for the negative side, the angle will be minus pi over 2. So the limits will be from minus pi over 2 to plus pi over 2. Okay, pi over 2. So in this case, okay, we will have very simple integration. So the integral of cosine theta is sine theta, and then when you put the result like that, k lambda over x times sine theta, now the limits is from minus pi half to pi half, you get a factor of 2, as you see. This is just 2. Why? Because sinus sine pi over 2 is 1 minus the lower limit, but sine minus pi over 2 is minus 1, so that 1 minus minus 1 is 1 plus 1, which is equal to 2. So it's just, and the result is 2k lambda over x. So basically what we have found that if there is a charge distribution along a wire, okay, later these charges will move and create the current, but now they are just hanging there. So if the distance is x, the electric field is totally in this direction, and the electric field is given by just k lambda over x, 2k lambda over x, okay, I, because this is x direction. So this is the electric field due to a very long wire, okay. Now we just modify this problem and see what happens if we have another case. For instance, suppose that we have a finite length, okay. Suppose the length of this wire is just L, and the charges are again distributed like that, and this is our x, and this is our y. Now the length of this thing is L, and again we do the same thing. We consider a small segment dy, and inside dq, and this produces an electric field like that, okay, dE. But now this dE vector will have both positive and negative components, okay, positive and negative components. So if this angle is theta, as you see, again, this is x and y, okay, and this is r, and what r is given here, okay. So this will have both x component and y component. So this is dex, as you see, dex in x direction, and this is dey, okay. So now since dex is just de times cosine theta, okay, and dey is equal to de sine theta, okay, de sine theta, we have now the electric field, which is given by, okay, k dq, integral dq over r squared, okay, times the x component, which is cosine theta I minus sine theta j, as you see. Now this is two-dimensional integration. Earlier we had only this part, but now we also have this part with a minus sign. Why? Because the y component of this small electric field is downward in minus y direction. So what we have to do is just this. So when you look at these cases, okay, and do exactly the same thing, use this kind of geometry, instead of solving in terms of y, solving in terms of angle, we see that the whole expression turns into this, okay, E equals k integral, okay, k lambda over x, okay, integral sign cosine theta d theta I minus sine theta d theta j. Very simple integrations again. Now the angle is very important, okay. This limits for these angle is the first angle, as you see, this angle is measured from the x-axis. When you're here on the lower end, this angle is 0, but when you are here, this angle is, suppose that the length is this much, so the maximum angle that you have is theta 0. So from 0 to theta 0. So what is the theta 0? Okay, what is theta 0 in terms of other quantities? Tangent of theta 0, as you see, is just x over y, okay, x over y, but the total length, which is L. So this is the maximum angle, and this is maximum length, which is, so instead of theta 0, I can write this, okay, or theta 0 is the arctangent of x over L, okay. So I can also write this. So instead of that, if you take the integral, you will have now the electric field which is given by k over x, okay. Cosine theta will give you sine theta, but sine theta is a 0 value at lower limit. So sine theta 0, when you put the upper limit, you will have this I, okay, plus now sine theta will turn into cosine theta. The integral of minus sine theta is cosine theta, but the lower limit cosine 0 is 1, and upper limit is cosine theta 0. So cosine theta 0 minus 1 times j will be exactly the result. So this electric field, as you see, has two components. One, this component, and the other this component, okay? So for our previous problem, this theta 0, remember that the maximum angle was 90 degrees, sine 90 was 1, but this gave us 0 because cosine 90, okay, cosine 90 is 1, but 1 minus 1 is 0. So for this symmetric problem, this is exactly giving you 0 for the second part, so that the electric field was totally in x direction. But for our case now, the electric field, okay, electric field direction is going to have two components. This, okay, since cosine theta is always less than 1, as you see, and there is a minus 1 there, negative component is always going to be minus. So the electric field for this one, the total electric field for this one can be given only in terms of this. As you see, sine theta 0 can be written here, because sine theta 0 is just nothing but, okay, y over r, but cos y over, right, instead of y, we have to use L because it's the maximum angle, L over r, but cosine theta 0 will be equal to, okay, x over r. So you can insert L over r for sine theta here, okay, and then x over r for cosine theta 0. As you see, they have now y inside. Why? Because sine theta 0 is x over square root of x squared plus y squared. And this will be also a function of y through this expression, because r is square root of x squared plus L squared plus x squared, okay? So, right, L squared plus x squared, and this is L squared plus x squared. As you see, the electric field will be totally a function of x. However, when you want to find the electric field at a segment like that in dy, it will be a function of y. We will use this height. But when you consider the total length, which are the limits in this integration, then we will have this case. Again, the electric field will be totally in dependent on the x direction. However, it will also be dependent on the length of this wire, which is L. Okay, so this is the end of recording for this example. And then I will let you ask you some questions.